Hi everyone. Today we're doing notes for 11.3 combinations. 5 people who were made iconic by death were Marilyn Monroe, James Dean, Jim Morrison, Janis Joplin, and Jimi Hendrix. Imagine you ask your friends, of these 5 people, which 3 would you select to be included in a documentary featuring the best of their work? You're not asking your friends to rank their 3 favorite artists in any kind of order. They should merely select the 3 to be included in the documentary. We are interested in which artists are named, not the order in which they are named for the documentary. So, a combination of items occurs when the items are selected from the same group, in other words, the 5 stars who were made iconic by death in this case. No item is used more than once. You may view Jimi Hendrix as a guitar god, but your 3 selections cannot all be Jimi Hendrix. And the order of the items makes no difference. I'm going to underline this. The order of the items makes no difference. Morrison, Joplin, Hendrix is the same group in the documentary as Hendrix, Joplin, Morrison. Okay, so as a recap, a permutation is problems that involve situations in which the order matters and a combination has problems that involve situations in which the order of the items makes no difference. Now, one thing that I like to do is I'm going to draw a little mini picture for you. If we're talking about ice cream, for example, let's say we have 2 ice cream cones and we have 3 flavors, right? We have a strawberry, we have a mint chocolate chip, and we'll call the blue Superman. And so if I have these 2 cones, in this case, this is a permutation in which the order matters because you have to eat the ice cream that's on the top first. You have to eat top down. You can kind of eat a little bit maybe off the sides, but for the most part you have to eat from the top down because if you were to eat the one at the bottom, the ones on the top would fall off. Okay? Now, if instead we are looking at a bowl of ice cream, here's 2 bowls of ice cream. This is an example of a combination in which the order you eat them does not matter. We don't have to worry about our ice cream falling over. It's all just in the bowl, so you can eat any one of them first, second, or third. Okay, so the first thing we're going to do is distinguish between permutation and combination problems. So it says for each of the following problems, determine whether the problem is one involving permutations or combinations, and it's not necessary to solve the problem. So A says, how many ways can you select 6 free DVDs from a list of 200 DVDs? B says, in a race in which there are 50 runners and no ties, in how many ways can the first 3 finishers come in? I want you to take a minute and decide if these are permutations or combinations for A and B. Okay, so for part A, This is a combination because our order does not matter. You're selecting 6 free DVDs. It doesn't matter which one you pick, first, second, third, fourth, fifth, or sixth, right? They all just go in the bag. You get free DVDs. For B, this one is a permutation because the order or the place matters. It'll make a big difference for someone if they win first place in the race versus if they win third place in the race, or if they don't place at all, okay? All right, similar to permutations, the notation NCR means the number of combinations of N things taken R at a time. So we can develop a formula for NCR by comparing permutations and combinations. Consider the letters A, B, C, and D. The number of permutations of these 4 letters taken 3 at a time. So again, we want permutations of our 4 letters taken 3 at a time. This is 4P3. So this is 4 factorial divided by 4 minus 3 factorial, which is really just 1 factorial. So this is 4 times 3 times 2 times 1 divided by 1. So my 1's cancel. And my 4 times 3 times 2 gives us 24. So now we're actually going to list out these 24 permutations. And so you can see I gave you each of these. But if you notice, all the ones in the top row represent A, B, and C, just in different orders. All the ones in the second row represent A, B, and D, again, just in different orders. The third row all represent A, C, and D, but in different orders. And the last row all represent B, C, and D, but in different orders. So you see there are 24 permutations of these letters, but there are only 4 combinations when the order doesn't matter. So because the order of items makes no difference in determining combinations, each row of 6 permutations represents 1 combination. So there's a total of 4 combinations. Thus, 4C3 equals 4. So there are 6 or 3 factorial times as many permutations as there are combinations. So our combination, this is the number of possible combinations of n things taken r at a time. Our formula is going to be NCR is equal to n factorial divided by n minus r factorial times r factorial. And for reference, our permutation formula again is NPR, and this is n factorial divided by n minus r factorial. So again, when the order makes a difference, permutations, there will be more of them. The combination, when the order does not make a difference, there will be less of them because you're dividing by this extra r factorial. Okay, so here are some more problems. This one says, you volunteer to pet sit for your friend who has 7 different animals. How many different pet combinations are possible if you take 3 of the 7 pets? Go ahead, take a minute and see if you can figure this one out. Okay, so there's 7 different animals and you take 3. So it's 7C3. So 7 factorial divided by 7 minus 3 factorial times 3 factorial. So on the top we have 7, 6, 5, 4, 3, 2, 1, divided by 7 minus 3 is really 4 factorial. So you have 4, 3, 2, 1 times 3, 2, 1. So I'm going to cancel the 4 through 2, 1 with 4 through 2, 1. And then this 3 times 2 times 1 cancels with the 6. So that leaves me with 7 times 5, which is 35. Our next one, how many different 4-card hands can be dealt from a deck that has 16 different cards? Go ahead and do this one, please. Okay, we want 4-card hands, and it's being dealt from a deck that has 16 different cards. So it's 16C4. So this is 16 factorial divided by 16 minus 4 factorial times 4 factorial. This is really 12 factorial. So this is 16 times 15 times 14 times 13 times 12. And I'm going to do dot, dot, dot after the 12. Because I know in the bottom we have 12 dot, dot, dot. And then times are 4 times 3 times 2 times 1. So our 12 and lower will cancel. I know now I have 4, 3, 2, and 1. So we can cancel my 1. And I know I can do 4 times 2 is 8. So I can cancel that with the 16 and make that a 2. And I know I can also divide 15 by 3 and make that a 5 in order to completely eliminate my denominator. So that leaves me with 2 times 5 times 14 times 13, which ends up being 1,820. All right, our last problem. A zoo has 6 male bears and 7 female bears. 2 male bears and 3 female bears will be selected for an animal exchange program with another zoo. How many 5-bear collections are possible? Go ahead and try to do this one, please. Okay, so this one we actually have to think about in 2 parts. So first we have the male bears. We have 6 male bears and 2 are going to be chosen. So for our males, it's 6C2. So this is 6 factorial divided by 6 minus 2 factorial times 2 factorial, which is equal to 15 when we calculate it out. Then we have 7 female bears, and we're choosing 3 of them. So for my females, we have 7C3. This is 7 factorial divided by 7 minus 3 factorial times 3 factorial. And this ends up being 35. We did that same one earlier. Okay, so now we have to think about using our fundamental counting principle. Whenever we have 2 different things and we're putting them together for combinations, we multiply. So I'm going to take my 15 times my 35, and that will give me 525 possible combinations. And that's the end for today.